Hi, good morning, and I welcome you all to the CIT Quantum Hackathon 2022. And we are at our 20th session of the workshop series, and it is sponsored by IBM Quantum. So I'm so delighted to welcome Mr. Rupesh for as our guest speaker, and he has completed his masters in physics from University of Hyderabad, and he is a research intern at Delft University of Technology, and he has completed his intern as quantum applications intern at Data Economy Hyderabad, and he is also a Qiskit advocate and passionate about quantum computing. He has given many sessions regarding this, and so we are so excited to hear about the currency arbitrage using the quantum computers. And the session is all yours now, sir.
Thank you. Let me quickly share my screen.
Sure, sir. So your screen is visible, sir.
Okay. My screen is visible, right? Yeah.
Yes, sir.
Let me just get the laser pointer. All right. So, hi everyone. I'm Rupesh. I'm currently tuning in from Hyderabad. But as such, I'm also from Chennai. And in fact, I was born in Coimbatore. So it gives me great privilege to be giving this talk for Coimbatore Institute of Technology. So the topic I'm going to be talking on is finding currency arbitrage. But what exactly is this? So essentially, we have all these different currencies from different countries, and when we start to trade one currency for one other, usually there is only a loss because of transaction charges and things. But there are certain discrepancies that happens in essentially instability in the market, where sometimes when we go over a transaction loop by going from dollars to rupees to some particular series of transactions, we can actually churn a profit. But classically, solving this problem is NP hard, which means you can't solve this problem in polynomial time. And so this is the context in which I'd like to introduce this topic. So we have all these different conversion rates which change dynamically every day. And now there are certain disparities that, for instance, USD to AUD, with the Australian dollar, the down conversion and up conversion are not exactly reciprocal to one another. Sometimes going from USD to Australia is cheaper, sometimes it is more expensive than going the other way around. And so all of these discrepancies can sometimes be used to churn a net profit out of the system. But our goal is not just to find a cycle that finds some profit, but rather to find the cycle with the highest profit. So the way to go about modeling this problem is to first construct a graph. So here we have a graph of the problem. So what do we have here? We have these vertices, which are essentially the different currencies that we have. And all of these currencies are interconnected by certain conversion rates. And if you can notice, you will see that these graphs are bidirectional. So there is arrow going from USD to francs here, but then there'll also be another conversion rate going from this point to this point. So this is a highly dense and densely connected and bidirectional graph, and the number of possible loops in such a cycle grows exponentially. And so the idea for us is to find a loop of transactions. For instance, this transaction I've highlighted here could be the most profitable loop of all the cycles that we can draw on this graph. And so how can we solve this problem? Now, the classical way, using classical computers, we can solve this problem by a sort of a brute force approach. We list down all of the cycles. We go over each cycle in the graph, and for each cycle, we evaluate what is our current profit. And we can just keep doing this. But what happens is, if you it's fairly easy to show that the number of possible simple cycles grows exponentially with the number of currencies. So if you are considering more than 20, 30 currencies, the problem goes easily out of hand. And so this is why we might want to consider a quantum approach to solving this problem. So the quantum approach to solving this problem has a bunch of different steps. So I'll just have a overview over in here. So I'm sorry for the train sound. I actually live close to a railway station. Anyway, so what we do is we map each of the edges between currencies to a qubit, and we create a quantum circuit like that. So we have for each possible edge, which is the number of edges that we have here, and that is basically the number of currency conversion rates that we have. And for each currency conversion rate, we have a qubit associated to it, and then we have to somehow encode the net profit that we can get from this system as an optimization problem and apply whatever constraints are necessary. And once this difficult part is done, we can transform this problem into a cost Hamiltonian and solve it variationally. So this is roughly the overview of how we are going to approach this problem. So the first step is to, of course, map qubits to the edges on the graph. So as you can see, there are many edges on this graph, and each edge is associated with a particular qubit, as I've shown here. And this number of qubits required grows only quadratically in the number of currencies rather than exponentially, which is where we are going to find an advantage in using quantum computers. And once we have done this mapping, we can generate these circuits, which would essentially try to find the most profitable loop. But how does this work? But before we go to that step, let's think a little bit about the mapping itself. So I've just shown you about a couple of examples as to how exactly this mapping works. So we have here only three currencies, and so we only have three edges connecting them. Of course, this is for the simplistic case where there is symmetry between the conversion rates. In reality, there will be two edges connecting each vertices. That is because of the down conversion and up conversion not exactly equal. And so for different state kets that we can possibly have, we have these different graph coloration that is possible. But note that not all of these possible paths are actually valid paths. For example, if you take a look at this one, this is not a loop. This is an open-ended graph. And so we start from one currency, we go to another currency, and then we are stuck here. We are not coming back to our original currency. So the only valid loops in this particular case is this one, where we go from this currency to this and then back again, and all the other similar single qubit, single register cycles here, and also this full cycle here, which is also a valid solution for our problem. And so keeping this in mind, we have to encode a profit into our quantum circuit. And so the profit that we want to get itself is coded in this little formula that we have here. So I'll try to explain what exactly this formula means. And so what you see inside the summation is sum over xij, which is essentially the qubit measurement result, or basically whether or not an edge is included in the most profitable loop. Putting this in context, if we take a look at this one, let's say this edge, if we call this as the 0 and this as 1, then this connection from here, this could be called x01. And whether or not x01 is part of the most profitable loop is coded by the binary variable true or false. And so we have similar ones for all of them. And note that 01, x01 and x10 are not necessarily the same. We could have this edge within the most profitable loop, whereas we may not have this in the most profitable loop. And so with that in context, we can, so this xij, that is what that represents. And then the Cij essentially represents the conversion factor itself. We have a currency I and then a currency J. Let's say if these are Indian currency and United States dollar, then C has a value of roughly 80 rupees. And the other way around would be somewhere close to 1 by 80. So these are the Cij values, which are the conversion rates. So why does this formula work? So I've expanded out the formula for a simplistic case here. And so we start with the currency 1 and go convert it to 2. And then from 2, we go to 3. From 3, we go to 4. And from 4, we go back to 1. So this is essentially a cyclic loop, and this is exactly what the summation here means. And so when we sum over this is a simple log. If you have a sum of logs, then that's the product of the coefficient, or not the coefficient, the value that you're taking the log of. And ideally, in an ideal case scenario, this product should be one or less than one, because we're starting with $1, let's say, and at the end we are going from some other currency back to dollars. And in an ideal world, this would be exactly one, and so the log of that would be zero. However, for certain discrepancies that happens in the market, this product can be greater than one. And so the log of that is not equal to zero, but a positive value. And that positive value, the greater that positive value, the more the profit that we can extract. And so essentially what multiplying these conversion rates here imply is essentially something like going from one to the next currency and then finally coming back to the original currency, which is reflected by having one both at the end as well as in the beginning. And usually this value could be just you start with a dollar and you end with a dollar, or maybe less because of transaction charges. But at some times we can churn a profit out of it. And so that is the quantity that we want to maximize. And we want to maximize that over all possible, over all the paths in a particular cycle. So E is basically all edges in a given cycle, and we want to maximize it over X, which is the binary variables 1 or 0, which essentially tells us whether a particular conversion rate is part of the profitable loop or it is not part of the profitable loop. And so this is how we end up with a discrete optimization problem. It is discrete because we have this xijs, which takes values only 0 and 1. So we cannot optimize this using some kind of a gradient descent kind of an approach, because when you have discrete values, you can't define a gradient. Right. Now, apart from the cost function itself or the profit function that we want to maximize, there are also certain constraints that we need to place on the possible solutions, as we just showed a while ago. And so, what are these constraints? The first constraint is something called as the flow constraint. So, what does this mean? Given any transaction loop, it must actually be a loop and not an open-ended or discrete separate edges that are highlighted. So we need to be able to traverse in this path by going from one currency to the next in a continuous loop. And we need to start and end at the exact same currency, because only then we can actually talk about a profit. Because if you start at one currency and end with a different currency, the conversion rate between the first and last currencies itself can keep changing. So you never really know if you made a profit or a loss, and the profit or loss can change with time. And we don't want that uncertainty. So if I start with a dollar, I want to know that I have $1.1 or $1.2 or what exactly is that number. And so the flow constraint essentially emphasizes that. And the way it does it is for all possible edges within a given cycle, we sum over j, and that should be equal to the reciprocal. And so what this really means, what this emphasizes is that if you are suppose in this, but this here I've shown two different examples of the adjacency matrices of those graphs. And so this is roughly the I index on the rows and j index on the columns, and the xij values are given within the matrix. And so when I say 1 here, it means that the conversion going from the second currency to the first currency is part of the loop, and the conversion going from first to second is also part of the loop. And so this is just a simple loop that goes from currency 1 to 2 and then back to 1 again. So a simple loop with just two currencies. But if you take this example, here we go from the third currency to the second currency, and then we hop from second currency to the first, but then that's it. We don't have a hop from first to the third. So then this can be modeled, this can be thought of as a hopping where you go from 3 to 2 and 2 to 1, but then you're stuck there. You're not going back to your original currency. And so this can't be a valid solution. And so we need to make sure that such solutions are not part of our final answer. And so what we do is we take this constraint and we take this guy to the other side and make sure that this value has to be equal to 0. And so we can enforce that constraint by basically, there's a tool within Qiskit to do that. But roughly the idea is that you square it and then you have a constant factor here, so that if a particular solution violates this condition, it receives a huge penalty. And another constraint that we need to impose is this one. It's called the no repeat constraint. And so what this implies is in any given transaction loop, any particular currency can only appear once in that loop. Now, why is that a condition? Now, as such, if you think about what we want to do by finding these kind of currency loops, is that we want to keep trading in them. If I find one currency loop, I will not trade once in that, but as long as the arbitrage exists, I will perform 100 such loops and churn out a maximum profit. But now let's consider the case where you have a loop with three currencies that is giving you some small profit, and then a loop with five currencies that is giving you a much higher profit. But if we allow for currencies to be repeated in our solution, then the smaller profit loop we could get a solution where the smaller profit loop is actually repeated 20, 30 times, making it look as though the smaller loop is actually the more profitable one. And so, to avoid these kind of silly solutions, we need to make sure that we are always focusing on the simplest cycle. These are called simple cycles within the language of graphs, where when you're drawing a cycle, they only go through a single, they go through a single node only once and not intersect their own path. And so this condition enforces that. As a slightly different condition. It's not an equality condition, but then a less than or equal to kind of condition. But the way to enforce it is fairly similar. You take the one to the other side, you square it, and then you add it to the cost function itself. And here we have these two examples showing exactly that. Now, this is a good, reasonable transaction. You go from 3 to 2, 2 to 1, and then you have a loop that goes from 1 to 3. And so you have a good loop going on here. We have no problems. But if you think about this graph, what this looks like is you're going from 1 to 2, and then you're going from 1 to 3. So you have one currency from which there are two branches. That is not how we are going to do trading. We are going to go from one to the other, and from that, we're going to jump to a different currency. And so this solution is not a valid solution. And just to remind you, these are the E is the all the edges in a cycle, and Cij is the conversion rate, and Xij itself is 1 if it is part of the profitable loop, and 0 if it is not part of the profitable loop. All right. Now, although I've kind of gone over the mathematics necessary to enforce all of these conditions, QScript actually does this for you. And it'll actually even print a nice summary of what kind of a optimization problem you have set up. This is all available within QScript optimization Python package. And so you can mention what your profit loop should be, and I mean, profit function should be, and then you mention the constraints. And so here we have the currency arbitrage problem. And this is essentially the profit function, the log summation that we talked about. And then we have the no repeat conditions. We have four of those because this particular case, we're talking about four currencies. So the matrix itself is a 4 cross 4. And so you need to emphasize four of these conditions. And similarly, we have four flow constraints. And these are the binary variables that whose values we want to find out. Okay. And so QScript will take care of the math also for converting this constrained problem into an unconstrained problem. So at this point of time, quantum computers can only take in inputs QBOS. QBOS is a quadratic unconstrained problem, essentially. So to remove the constraint, we take each of these constraint terms and we add it as a penalty term to the function that we want to maximize or minimize. So if you look at this one, this has changed from a maximize to a minimize function, which would mean that a negative was multiplied to this maximize profit loop that we initially had. And then these other things were added by taking everything to the left-hand side and squaring and adding them along with a cofactor, ensuring that if any of these constraints are violated, we get a huge penalty, so much greater than the profit we could get from violating this condition, because this needs to be ensured, because if the constraints are weaker than the function we want to maximize, it will give us a solution so that the profit is maximal, but it might not be the best possible solution as I just described. Right. So we've covered a bunch of different things already. So the first step is to map graph edges to qubits on a quantum circuit, and then we need to encode the profit as a discrete optimization, and then we apply the necessary constraints that we talked about. So, are there any questions at this point? I can quickly take them, and then we can proceed further. Am I audible, right? Dharani, am I audible? Hello. Okay. I'm audible, right? Okay, cool. I'll get back to the presentation. Okay, if there are no questions, I will continue. So we have covered the first three of the steps that I have listed here. So what's the next step? All right. So now we have with us a bunch of we have a function that we want to optimize, and the variables of the function are all discrete. And so we have this discrete optimization problem. But if you carefully take a look at this, some of these problems have two coefficients. Sorry, some of these terms have two coefficients, while others have only a single coefficient. And so this essentially corresponds to certain quadratic terms in our optimization function, as well as some linear terms that we have. And so within Qskit, there is a simple way to extract the quadratic and linear terms. But as such, not a very hard task to do. Any kind of symbolic math library like SymPy or Mathematica can do this for you. And so we extract this quadratic terms as well as the linear terms and store them in two matrices called the Q matrix. And then we have the C matrix. C is a vector, sorry. So this Q is the quadratic term and C is the linear terms. And so this, what we have here represents the net cost function. So the quadratic term multiplied with x and on x and x square. So this is a matrix, and so we have x transpose and x acting on it, and then the linear term acting on x. And so this essentially is what our cost function initially is. Now we want to take this into the quantum domain, and like, so how do we do that? And so we have this cost Hamiltonian, and the way this acts on our any given state vector, that is what we need to find out. And then we also have this mixer Hamiltonian. So why do we have these two different Hamiltonians? This will take us to a quick prelude to what adiabatic quantum computing itself requires. Initially, I'll skip a few slides and go to this part quickly, and then we'll come back here. My laser pointer is missing. Right. So what happens in an adiabatic evolution is that we have initially our guess Hamiltonian, which could be called the mixer Hamiltonian. And then we have the actual Hamiltonian whose ground state we wish to find out. And the way we do this is we start with the ground state. Our initial state is the ground state of this mixer Hamiltonian. And then we change this parameter s of t ever so slowly so that there are no level transitions or something like that. So we need to make sure, we need to make a small delta t movement, and then we need to wait for it to equilibrate, and then we move another delta t. And so we do that very slowly, and then after a sufficient time, what we'll find is that we have successfully moved on to HC, and in the process, we have perturbed the initial ground state, the ground state of the mixer Hamiltonian, into the ground state of the cost Hamiltonian. So this is essentially how adiabatic annealing essentially works. So for instance, D-wave computers do exactly this. So initially we have S of 0 as 1, which means initially the Hamiltonian is the mixer Hamiltonian. And as time progresses, the contribution from HM reduces while the contribution from the cost Hamiltonian increases. And if we do this carefully and slowly, we can evolve our ground state, which is initially a ground state for the mixer Hamiltonian, to a ground state which is the for the cost Hamiltonian. Now, of course, the way this we apply this, we need to use totalization, not to simplify, and apply this for quantum computers, the kind of computers that use gates rather than the annealing systems. So if you're focusing on any of the quantum computers by IBM, then we need to actually totalize the system, totalize the Hamiltonian, so that we have physically implementable gates. So we'll get back to that. And so that's why we have these two different Hamiltonians, the cost Hamiltonian, which is the Hamiltonian whose ground state we wish to find, and then this mixer Hamiltonian, which will be the initial Hamiltonian that we'll be taking. And the ground state for this simple Hamiltonian, which is only just a bunch of X gates, is the plus state for how many of our qubits that we have. And this is, as you all know, we get this by applying Hadamard's on every single qubit, and this is the uniform superposition of all possible kets. Right. So how do we go from this xj, xi from our cost function to something that is quantum representable? And so we use this fact of the eigenvalues of the z gate or the z basis, which is the basis that we perform measurements on. So when z acts on a particular single qubit state, it gives you this value. And so what does this mean? Let's say if x is 0, then minus 1 to the 0 is just 1. And so if the z gate is acting on the 0 state, you will just get the 0 state. But on the other hand, if z is acting on the one state, you get minus 1 to the power of 1, which is negative 1. And so the action of the z gate on the one state will give you minus 1. And so this essentially encodes that. But this itself can be simplified for binary algebra into 1 minus 2x. Because there are only two inputs, we can quickly verify this. If xi equals to 0, then this function should give us 1. And so if you put xi equals to 0, this is 1 minus 2 into 0, which is 1. And if xi were 1, it should give us minus 1. And so if you put xi as 1, we get 1 minus 2, which is minus 1. And so within binary algebra, we can actually simplify minus 1 to the x into 1 minus 2x. And so if we take this and we rearrange the elements so that we can get the action of xi on a given state vector get x. And so by just revolving the terms, we see that the action of xi on the get x is exactly this gate, the identity minus zi divided by 2. This is the same as xi. So if we go back to our cost Hamiltonian, we had all these xi and xj's. So this xi for inch here has to be replaced by identity minus zi, and this xj should be replaced by identity minus zj. And similarly for all of our other terms. And if we do that, we end up with a cost Hamiltonian that looks something like this. And so we have our qij's, which is our quadratic terms, and then we have the zz gate, and then we have this z gate with a combination of the terms. This comes because of the identity that we have, and so we'll have these cross terms which have exactly one z gate, and then we'll have this constant factor which just corresponds to an identity. And this constant factor can be ignored because any Hamiltonian is only is true up to a overall constant. So you can add a constant factor to all the energy in the universe and nothing will change. So with that thing, we can actually get rid of this final term that we have here. All right. So we have this cost Hamiltonian. And so if we have a Hamiltonian, we need to exponentiate it in order to get the unitary, which we can apply on our quantum circuit. And so we need to exponentiate this Hamiltonian, which is the matrix exponential. And if we do that, we have the ZZ here, which when exponentiated, we get the RZZ gate, which is the controlled ZZ gate. Sorry, not the controlled, the parametrized ZZ gate. And then similarly for the Zi poly term with this prefactor, we have the RZI, where this with the angle itself is determined by what were the coefficients in our initial cost function. Right. So with those transformations, we have a cost Hamiltonian whose unitary we have found out. And similarly, we have a mixer Hamiltonian, and this is fairly simple to construct to exponentiate the x gate, which gives you the Rx gate, the parameterized x gate. And so we have the two unitaries that we are interested in. But if this were a adiabatic system, we'd be done here. But really, we are on a universal quantum computing kind of a system where we have a bunch of gates, and we can't really implement any given Hamiltonian that is provided. And so we need to convert these these unitaries into unitaries that can actually be implemented on the circuit. How do we do that? There's a process called totarization. You might have heard of it in other talks in this session. And so what that essentially says is that if you have exponential of the sum of two matrices, then that can be resolved into the product of them in the limit that we divide by n. So we make small incremental steps, delta. So delta t is essentially t by n, and then we apply that small delta t increment n number of times, and if this n is taken to infinity, then that is exactly the gate that we wish to implement. And so coming back, we have this cost Hamiltonian and we have this mixer Hamiltonian, and the two of them constitute the total Hamiltonian in the following way, where you have this S of t parameter, which is how we evolve towards the final ground state. And so, what we really need to do is we need to exponentiate this full Hamiltonian. And most often, we really have any kind of gates that can implement exactly this unitary. And so, we need to break it down. And to break it down, we use this totalization formula. And of course, n tends to infinity is an impossibility for practical cases. Most of the time, I see myself using n equals to 3, which is actually quite low, but it seems to do the job. We get quite accurate results for even just n equals to 3. So this is the number of layers that people talk about in a QAOA algorithm. And then finally, we solve this problem variationally. This is something a lot of people have talked about in the same talk. I heard, I think, Vishnu's talk. He was talking a lot about the variational methods in quantum computing. And so we use a very similar approach. We have the answers and everything set up, and we have these alpha and beta, alpha and gamma parameters, which are essentially the step sizes that we take in this abstract Hilbert space. Because in an adiabatic systems, we know which track we are going. Nature takes care of it. But since we are totalizing it, we're not entirely sure how much do we move in one direction and how much do we do move in the other direction. And so that exact question, we make it into a optimization parameter. And so we run this variationally between a classical computer and a quantum computer and optimize these alpha values, which are essentially the steps it takes to go from the ground state of the mixer Hamiltonian to the ground state of the cost Hamiltonian. And that is it. That's all I have for today. And so we can run this on quantum computers, get our results, and find out the most profitable loop. Uh, any questions? Okay. Think there are no questions right now. So you can always contact me either on LinkedIn or on Twitter. I'm available. You can connect with me, and if you have any questions about particular things that I explained today, you can reach me out on there, and I'll be free. I'll be happy to explain any questions you might have.